Okay, very good morning to all of the respected professors and PhD students, MSc students from various universities and institutes. So I, Pankaj Dhiman, PhD Research Fellow in HP University Shimla, hosting this event, and I heartily welcome you all. And I feel privileged to extend my warm welcome to all of you in the DAE-CVRaman lecture hosted by Department of Physics, Himachal Pradesh University Shimla, in association with Indian Physics Association and Board of Research and Nuclear Science. So this series is running continuously, I think, from last 30 years. And today we are having a lecture on harnessing chaos to be delivered by Professor Sudeshna Sinha from ISER Mohali. So we are having the chairperson of the Department of Physics, Professor Veer Singh Rangra. So I request him to please inaugurate the session and say a few words about the department. So over to you.
Okay. On behalf of the Department of Physics of Himachal Pradesh University, I welcome you all here. Though the webinar is being held through this online series because of this pandemic, it would have been much better in case had it been held lively here in the department, because of the present situation, it is not possible. Even then, our department is feeling privileged and highly obliged, thankful for hosting this webinar on DAE-CVRaman lecture series being organized by IPA. And especially, I welcome and thank Professor Sudeshna Sinha ji for making her valuable time provided to all of us here in the Department of Physics. Ma'am, I would like to let you know something about our department. Ever since the inception of this Himachal Pradesh University, our Department of Physics has also come into being. It has been working rigorously and intensively since 1971. Presently here, our department is running MSc course, MSc Physics course, and MPhil as well as PhD. Though from the next session, the MPhil, as per the guidelines of the new education policy, MPhil will not be run by the department, but presently here, there are 15 students who are pursuing MPhil in our department, 45 students in MSc first year and 40 students in MSc second year. They are pursuing MSc, and around 40 students are pursuing PhD in different different disciplines in our department. So far as the faculty members are concerned, we are 7 faculty members. Out of these 7, we are 7 are the faculty members who belong permanently to this department, to this Himachal Pradesh University, and all are professors. And one faculty member, Dr. Amarjit Singh, he's on the basis of this faculty recharge scheme being introduced by the UGC. He's also here for the last 4 years. Of 7, we are undertaking this theoretical and experimental condensed matter physics, means material science field. We are working rigorously here. Also, we have honor that our fellow teachers are also working hard in the field of nuclear and particle physics. So yeah, we can say that we are working in theoretical and experimental condensed matter physics, as well as particle and the nuclear physics. Though we are very small in number, but the work being undertaken, work being done by here is of very good quality. And so many projects have been awarded till now to our department. So once again, I welcome you all here, and especially Professor Sudeshna Sinha ji for coming here to deliver a lecture here. And I make this this webinar open for everyone here who has joined through this link. So once again, I welcome you all here.
Thank you very much, sir, for inaugurating this event and sharing the words about the department. And I would like to add something in the events that are being held in the department. So our department has hosted many events in the past, from national to international conferences, workshop, short-term courses, and also invited lectures. So we are happy to host this DAE-CVRaman lecture series. Uh, so now I would like to invite my PhD supervisor and uh, the you can say the leader of this event, Professor Shashi Dhiman, to please give a brief introduction about Indian Physics Association and also introduce our today's speaker, Professor Sudeshna. Sir, please.
So thank you, Pankaj. I'm audible to you?
Yes, sir, you are audible.
Okay, okay. So Professor Sudeshna Sinha, Professor Beat Singh Rangda, Professor Harlin Dhaya, and all my esteemed research scholars, and our MSc students. So I welcome all of you for this webinar. This is a wonderful initiative by Indian Physics Association, and shortly we call it as IPA. So I'm supposed to introduce you the IPA. So IPA was founded in 1970 with the objective for the creation, dissemination, and the application of the knowledge of physics. Publication. So they have publications, bulletins, reports, newsletters, and other, you see, arranging seminar like this special program lecture for physics community at large across the nation and outside as well, as per their you see understanding with the various country. So if I look into the status right now, IPA has approximately 45 chapters registered across the country with 3,500 members in India, and they have a special lecture series like DAE-CVRaman lecture series, right now we are hosting it. Another is IPA IOP, Institute of Physics Bhava, Cookroft Walton Exchange Lecture. So you see, Cookroft Walton Lecture in India, it is known as like this way, and in UK it is known as Homi Baba Lecture Series. Another, they have Professor P.A. Pandya Endowment Lecture. So for the younger people, I must introduce Professor P.K. Pandya. He was director of PRL, and he's a very eminent nuclear physicist across the country during his own time. And another special thing they do is they conduct recent series they have started. The pandemic is a webinar series, and
Excuse
the
me,
title
sir.
of that series.
Shashi, sir.
Yeah.
Sorry for interrupting, sir. Please, will you please turn on your camera?
Yeah, I can do that also. Yes.
Okay, okay.
I kept it because then the quality maybe audio goes. So it is okay. I think that's fine.
Yes,
Right?
sir. Yes, sir. Yes, sir. Please continue.
So you see, as I said that this is Professor Pandya's endowment fund. They have the webinar series, and the title of webinar series is New Horizon in Physics. Okay, so they host some awards also. So we have R.D. Virla Award in Physics, then Murli M. Chongain Memorial Award for Excellence in Applied Physics, then P.K. Younger Memorial Award for Excellence in Experimental Physics. So for the students, you see the name I have just now spoken, they are the eminent physicists across the nation during their own time. So the awards are naming, you see, given name under. So there are certain group, they are generous and they, you see, fund these awards. They have Young Scientist Award also. This is again, you see, funded by IPA. Then IPA has very best practices, that is for the best thesis award in the different disciplines of physics. So for example, in nuclear physics, they have a best thesis award. Then they have in high energy physics and short status physics. So you see, when DAE conduct their symposium annually, then the various research scholars across the country, you see, submit their thesis abstract to the DAE, and then they make a presentation during their participation in the DA symposium in a location. Then their best thesis is awarded every year. Okay. And they have publication, as I said in the beginning, through their objectives. And I have a humble request to all of you to become member of Indian Physics Association. You visit the website, and in website you'll find full detail of it. And today I'm very happy and delighted to introduce our speaker, Professor Sudeshna Sinha. She got educated at IIT Kanpur, then PhD from TIFR, and she was working in math science, and that is in Chennai. This is one of the DAE prominent institute for mathematics. And right now, since 2010, she's working in IISER Mohali, and she's a deputy director also there. She's eminent physicist, and we are very happy to IPA rather. You see, they contacted Professor Sinha for delivering a lecture at Shimla. So, ma'am, you are welcome, and we are very happy. So, Professor Manoj Sharma has also joined to us from Thapur Institute of Engineering and Technology. He was former head of the department there. So, welcome, sir. So thank you very much, ma'am. And now I invite you to start your lecture. Welcome.
Okay. So should I share the screen then, or
Yes,
I
ma'am.
should ask?
Please share.
Yeah, I'll do that. Yeah. So is it visible?
It is visible. So
it's visible, right? Okay, okay. And I'll put my speaker view as well. Let me put on my video.
Yes.
So you see me too, right?
Yeah, it's
okay.
fantastic. Yes.
Okay, great. Okay, so let's start. So let me first say, of course, thank you very much for hosting this lecture and the generous introduction. I really wish I could be there in person, and I do hope I get to visit your department sometime when the world normalizes. Right. So now today what I thought I'd share with you is one particular thread of my research interests. So this research thread actually is not to do with characterizing nonlinear dynamical systems. Rather, it is an effort to use what understanding we have to work in a specific application area, a very important one, namely computations. Okay, so this I would try to communicate just the basics of our broad efforts. Okay, so I know that this virtual audience is not an expert audience, and so I thought I would start with a very brief and somewhat shallow, necessarily, introduction to the concept of chaos, since this is one of the two words which are there in the title. So it does merit a few slides. My apologies to all the experts in the audience, of course, for the next 10 minutes. So one of the things which I always like to say, because it always amazes me, and to use or to paraphrase or put a spin on Eugene Wigner's famous quote, I'd like to start with the unreasonable effectiveness of classical mechanics. So it's a very old formalism, but it has stood the test of time. And what is amazing about it is that it is mathematically rigorous, and it gives us a toolkit, which is not just, it's also extremely useful and still relevant. And the other part, which is interesting, is that it spans a huge range of scales. So, my friends who do nanomechanical oscillators also do, use the standard models of classical mechanics. And of course, the astrophysical objects naturally are described by this formalism. Now, what is chaos? So chaos, you can think of, is a new frontier of a very old science. So it's like the new kid in a very old block. So it is one of those concepts which made us rethink or reassess the way we view the classical physical world. So what was the surprise? What necessitated this particular paradigm shift? So what people noticed over time was that a very large range of seemingly simple natural processes seemed to be exhibiting enormously complex behavior. So it almost appeared as if this simple natural process was evolving under a very random force, or wasn't even deterministic. So in a nutshell, they were completely deterministic systems which displayed exponential sensitivity to initial conditions. So in practice, or essentially, they were unpredictable. So you don't think you will have a sentence which has determinism and unpredictability put together. But that is the delicious sort of contradiction that people started noticing and trying to come to terms with. So this necessitated a paradigm shift in understanding classical systems, which people thought they understood from the time of Newton. And the new science, or the new mathematics that was needed to understand it, is often called chaos theory. Now, the word chaos, of course, is used in commonplace. In fact, in India, we, of course, use it all the time, to describe everything from traffic to politics, everything is chaos. And so we know the word, it's there everywhere. But it's also a very old word. So it was there in old Greek cosmology as well. And it sort of referred to something which could be thought of as an abyss, or this primeval emptiness of the universe before things came into being. So before order, pre-order. So not order, but something which is leading up to something order. And apparently my Chinese friends tell me that there is also a Chinese symbol for chaos, an old Chinese symbol right here. And that one also sort of means the Greek meaning, as in pre-order. Okay, in the beginning, there was this chaos, which led to order. And if you look at the Webster English Dictionary, the meaning of chaos would probably come out to be confused, unorganized, disorderly state, which is what we used in commonplace usage. However, and that is the interesting part, this very common English word made its way into technical terminology. So it got inducted into scientific literature around 1975 or so. So people, it's that newer field that the word which describes the field came into literature around the 70s. And it was a paper by Lee and York. It was actually in the American Mathematical Monthly, and it was called Period 3 Implies Chaos. And this was the first time technically they used the word which they defined in this particular paper. And so what is the key idea? So I'll have a few slides, as I said, since I understand that the audience is general. So if I had to have a more popular way of putting it, the question would be, does God play dice? So what is the key idea? The idea is that the present determines the future of a deterministic system, okay, which is why we thought that the whole universe could be described like a clockwork universe. But, and this is the bad news, the approximate present does not approximately determine the future. And so one observes a whole lot of irregular motion coming from deterministic dynamical systems, which are so sensitive to the initial condition that they are impossible to predict in the long term. So they're impossible to predict unless you had infinite and perfect representation of the initial state. And I've put the word analog values for people, all who do numerical computations and who take differential equations and integrate it. They know the importance of representing a state with an analog value, and that was, of course, always have finite precision. And so this tells us that you cannot even approximately figure out what's happening in the future. And even luminaries much before 1975, when you first heard it in technical literature, people like Maxwell, Hadamard, Poincaré, when he was trying to address the three-body problem, they were bothered by it. They had unease about it. So they flagged the issue, but there was no resolution. They did not quite address it, but they knew that there was a problem there. And lastly, I have listed Lorentz, who was an atmospheric physicist in MIT. And his whole thing was, so he was the first person who noticed that this was a very big player in numerical simulations. So he was numerically simulating differential equations, and he noticed this extreme sensitivity to initial conditions, where, you know, we very casually, store our numbers with some precision, and then, you know, maybe start the calculation again from there, thinking, you know, nothing has changed. But he showed, and he was disturbed by the fact that things were drastically different. And so this thing was brought to light in one of the early papers of Lorentz in the 1960s. So now the concept, which is often popularly called the butterfly effect, sort of, exemplifying this sensitivity to initial condition, has caught popular imagination. It's part of common folklore. There are even Hollywood movies, The Butterfly Effect, which made some money, I believe, and bestsellers. For instance, The Making of a New Science by James Gleick, which tells you the early years of this particular theory, where people didn't know it was a theory at all. People were just trying to understand classical systems. And so these are nice, popular books on the subject. So let me now put in a slide, first, a simpler, but because simplicity, you lose some precision, but let me still put it, a simple, slightly imprecise characterization of chaos. So I would call it sustained, disorderly looking, aperiodic, long-term evolution, coming from a deterministic system, deterministic classical system. And so, owing to great sensitivity to small changes in conditions, the behavior of such systems is so unpredictable as to appear random. Okay, so something random looking is generated by a perfectly deterministic set of equations. And the more precise signature of chaos is given by this particular exponent, which goes by the name of Lyapunov exponent. The positivity of that one signals chaos in a rigorous sense. However, this is a pretty difficult exponent to estimate. You see two limits out here, t tending to infinity and the difference in state tending to 0. Both of these are quite hard limits to estimate, but this is the rigorous definition. But putting a mathematical definition is one thing, but I thought I'll show you two pictures. Nothing conveys things more than pictures. So I have been saying from the beginning that simple systems are giving complicated things, and that's the surprise. So because after all, you know, if I put hundreds of oscillators together and something very complicated comes out of it, you know, I might say, oh, okay, you know, I put complicated things, so complicated things came out. So fine. But this is not that. I have a very simple system, which you can do in your pocket calculator if you want. And yet, what will come out will look so random that you wouldn't believe that came from a simple system. So I have put three things here. These are dynamical systems which are called maps. So maps are systems where the time is discrete. So all continuous time systems can also be expressed as maps by Poincare sections. So it's not, it's not fundamentally different. But when I write it this way, you can see it as a simple form. So these three maps I've put. One is called the logistic map because it was modeling populations. It has one nonlinear term, which is, if you open this out, x square. So it has the simplest nonlinearity, quadratic. The second two actually are even simpler. They are piecewise linear. So the shift map is like two segments which are, you know, like straight lines. So these are mod 1. They are defined in a range 0 to 1 on the real line. And so anything which spills out of the real line is, you know, the remainder is put back. So mod 1. So they are like two straight lines. The tent map actually looks like tent. It has two linear segments, and at half is the top of the tent. Now, what is the action of this map? Why is it so interesting? One action is to stretch. So neighboring phase points essentially run away from each other. We will need that because we need exponential sensitivity to initial states. So we would need the trajectories to fly away from each other. But if two trajectories ran away to infinity fast, it's not interesting. What is interesting is that the operation also has a fold operation, which is this mod 1 or this quadratic non-linearity, which in fact makes it non-invertible, the map in technical terms. So what happens is that the iterates are then pushed back into a range. So locally they are running away, but globally they have to come back to the area. So it's very complicated. It's like you have to live with your neighbor, but you sort of want to run away from your neighbor. So, you know, the dynamics is there. And here is something which came out of from numerical simulations, which took like 2 seconds to run, very fast. So I just put in some number here, I think maybe at 0.1 or something. And I just put the iterates one after another up to 2000. So at each point, I've put a point. And as you can see, it looks a mess. So it looks so random. And yet look at what it came from. Just some number r. I have taken 4, r to be 4 in this particular thing. So this is 4x 1 minus x. You would have thought this is a very simple system, and this output is not expected. Here is a second example. This is called the Arnolds Cat Map. It is the last example was a non-invertible map. This is one non-invertible 1D map. This is an invertible 2-dimensional map. It also is an area preserving map. So it often is used to model Hamiltonian systems. So here is a pretty picture. So I have put pixels in a box 0, 1, 0, 1. So it's a box of side 1. And I've put a cat's picture just to make it cute and see what happens. I do one iterate of the map, just one, just to tell you how drastic it is. So what is the first action? The first action is stretch, as I said. So the first action is to stretch the box out because of this 2x here. And the second action is to fold because I have a mod 1, mod 1. So I have to cut up the pieces and put it back in the box. So you see, classical mechanics also has a cat in a box, but the cat is totally mangled and it's a very sad thing for the cat, but it's been pushed back into the box. And this picture then begins to look like this picture in one iterate. So that is the amazing part, that you have lost literally all information about this in just one iteration of one step of evolution of the system. And look how simple the system was. It was just xn plus 1, that is x at the next time step is just 2x plus y, and this y was x plus y. And I just did the mod 1 operation for the folding. So that is the power of these systems. Now, the main issue of this talk is to say this is lots of very new, very exciting classical mechanics. Now, is there some way we can use this knowledge to work for us? Okay, so that is the question that we will try to address now. Okay, since in some sense the field appears to have progressed enough that you can ask for payback from what you understand for applications, as enough understanding has come. So we are trying to flip the question and ask not what we can do for chaos, but what chaos can do for us. But in order to harness or to use or utilize these nonlinear systems, which look so rich because it seems to have like all kinds of things in it, but we want to use it in an efficient way, in a direct way. So we need to do something. So I will show two ways of doing it. The first one would be to use controlled chaos. Okay, so that would involve a method or an idea or a strategy to extract a lot of temporal patterns from the nonlinear dynamical system in a controlled way so that we can sell it to the engineers and we hope that they can implement it. Okay, they don't like things which are complicated. They don't like things which are not efficient. So the effort has to come from the theorists to provide that to them. The second thing, if I have time, I would like to indicate is how to use noise, which you can't avoid, and the nonlinearity together cooperatively to work for us. That would be great, right? If instead of suppressing it and asking noise to go away, which it can't, can we make it, put it to our team and work for us? So let me start with control. So here is a control scheme, which I had actually done very long ago, but it came back for the applications after, quite a few years. So this control scheme is something I call thresholding. It is extremely simple. Suppose I have a dynamical system. X is, say there's a variable, X, state variable of the system, could be anything, and that is evolving in time. Now, all my scheme does is, anytime X is greater than a threshold, that is my cleverness where I put it, I will push it back to X star. So it's like a Lakshman Rekha. So if it goes out, I pull it back to come within my limit. Okay, that is all. So when it's not, when it's under the threshold, it has liberty to do whatever it wants. Okay, so it kicks in only when it's above threshold. So the broad principle is called a dynamic range limiter, and the action is clipping this chaotic system to cycles, exact periodic cycles. So we had chaotic, very complicated, almost random looking temporal sequences, but I can do this small intervention and get a whole range of stable desired patterns out of it. That is the power. So why is chaos good? It is advantageous because it possesses this whole range of temporal patterns, which lends itself to clipping to different behaviors. So here is a small table. It's like a lookup table. So I have put the threshold and I have put it for that chaotic logistic map, this one here, this one. So it was such a mess, right? And all I've done is I have put this scheme in there at different levels. So as I change my level, I get different behaviors from it. So, if I set anything up to half, I get fixed points. So the whole chaos becomes a fixed point. It stays at steady state forever. Or between 0.5 and 0.8, it becomes a 2 cycle, which means it goes from x1, x2, x1, x2. Then it may be a 4 cycle, cycles through 4 numbers, 6 cycles, 7 cycle, 9 cycle, whole list. I have, like in my paper, the entire full list. Okay. And what has it given us? So it has given us a flexible pattern generator, because you can get this wide range of stable responses from that same chaotic system. So you had one little module, which was a chaotic element, and you just put whatever threshold you wanted to it, and it took avatar, whatever one you wanted, it behaved like that. And technically, if anyone in the audience knows dynamic systems theory, just one word for them, the chaotic system is actually trapped in a super stable orbit. So from being this random looking thing, not only have I controlled it, I have controlled it to a super stable orbit by this thresholding act. And also, the moment it crosses, you pull it back. So the transience or the latency is very short. I should add one more word about ergodicity. Ergodicity is the property which guarantees that the system will explore its full range of available phase space. And this very same property assures you, guarantees that the system will exceed threshold, initiating control, and so it will get trapped in some cycle or the other soon. Okay, so you're guaranteed control as well. Here is an experimental verification of this. So it's not just that I did the analysis. I had a map. I did my nonlinear dynamics, techniques, which are these set of analytical results, which were there first in, actually there in this paper of mine from long ago, a very long paper. But we had sort of introduced the idea in 1993. But it took me many years to actually convince a person to do this experiment. And Murali, who had a wonderful lab very close by, one day I was telling him I'm not finding anyone to do it. He said, "Oh, this looks simple." And he went back, and in a couple of days, he sent me these oscilloscope traces doing exactly what we had done in our analysis. So those were exact calculations from symbolic dynamics, which we gave that lookup table. And these are his experiments on circuits, which by just changing your threshold, we got a period. This is the fixed point. So, you know, there's just one dot, it stays here forever. Then there was 4 circles like that. There was, I think this one was 7, this one was 10, etc., etc. So whole like library of patterns, literally. And this was a slightly bulky experiment on his tabletop in his lab. But later on, years later, Morai's group in Japan have made CMOS IC chip of it, where they have put about 150 or 120 of these maps in one chip, and all of them were threshold coupled, and they were controlled. So not only can you do it in a bulky experiment, you can also do it in these nifty IC circuits. I'll just run through a couple of pictures now, just to tell you that was on a map. You can also do it for differential equations. Here is a particular nonlinear third order differential equation. And if left to itself, it gives this chaotic orbit. So as you can see, it doesn't look like a neat orbit. It's like a band, like a noisy band. But as you clip it, as you put this threshold control at different levels, you can get period 1, period 2, period 4, okay, depending on where you put your barrier in phase space. Okay. You can also do it with a double scroll chaotic Chua circuit, which this one some people have seen in their labs, this nice butterfly looking thing, which is also completely chaotic. But here too, if I do threshold control, I can get fixed points. So this whole thing will get controlled forever to a fixed point, or to a 1 cycle, or to a 2 cycle. Okay. One can also do it for more complicated systems or more scary systems like a hyperchaotic system. This is a very stringent test because these systems have more than one positive Lyapunov exponent. If you don't quite understand the technical thing, I will just put it like this. It has more than one direction in which it is unstable. So when this instability is in more than one direction, you feel that if I put a threshold in one variable, that may not be enough. That may not cut it. Okay. So the question is, can I threshold this high dimensional system with more than one unstable directions, that is more than one positive Lyapunov exponent? Can I rein it in by thresholding a single variable? That's the question. It's a hard ask. And here is the question. This is the hyperchaotic attractor projected. It's a 4D system. It's projected in a 2D plane. And this is the controlled orbit. So indeed, we found that we could do this in both experiments, because Murali also did a hyperchaotic electronic circuit. And he could control it to lots and lots of different exact cycles. Okay, so it's a very powerful technique. So now the question is, can we use this flexible pattern generator, this thing that we have, it seems to be powerful, to do something for us? What can we make it? What work can we put it to? Okay. So what has it given us? It has given us a rich variety of behaviors, which has given this versatile pattern generator. And now I want to use this flexibility and the versatility to implement a specific thing. I want it to do computational tasks. So basically, now I want to use a chaotic element to design logic gates, so that this logic gate can be flexible, so that it could be reconfigured to all kinds of logic if possible. Then we would have a nice, potentially powerful hardware. So chaos now for computation. So what is the hardware now? That is our threshold activated chaotic elements. Same threshold mechanism I said. I will call it the chaotic chip or the chaotic processor. And how would I program these elements? By fixing the threshold. And how will I fix the threshold? Such that it does a desired operation for us. So certain input-output relations have to be satisfied. Okay, so these are a bunch of papers. The first one was in this PRL in 1998, but there was a very nice write-up in Scientific American, which not written by us, but by somebody on this work, which is more readable, I think. So aim, as I said, is to implement basic logic gates flexibly using a chaotic element with the ability to switch between different operational roles. If I can do it, this will give me a dynamic architecture and serve as general purpose because I should get all the fundamental gates and also more flexible than the usual statically wired hardware. Like, you make it out of families of NANDs or NORs. Here you would have something which could be any old gate, hopefully. So here's an illustrative example. I work again with a chaotic map, though it's done for many, many different systems, just to illustrate. So I want to make a logic gate out of it. Inputs are X plus I1 plus I2 for this 2-input logic gate. Output is just defined by the threshold mechanism. If it is greater than threshold, output is 1. If it is less than threshold, output is 0. That's it. Now, I've put, just to remind everyone, the truth tables of some of the basic logic operations. NAND and NOR are in fact fundamental. You can build any circuit out of them, but I have put a whole bunch. If I want the same chaotic element to serve as any of these gates by simple change of threshold, I will actually have to find a solution to this bunch of equations. These are the necessary and the sufficient conditions for these gates to be implemented. And however, I must find solutions which will solve them simultaneously. So it is not clear a priori that your function will allow this solution. That is the question. Can you find out the class of solutions which allows this? That is the math part of it. And the interesting thing is that robust solutions exist only when the system is sufficiently nonlinear. And in fact, if it's chaotic, you can find all those solutions. So nonlinear dynamics gives you the richness, which allows you these solutions, and determinism, so that you can work backwards. So you can do the planning exactly. And you can select out from each of this module, from the same module, all these different responses. Okay, so this is a bunch of patents here which work on this, and indeed here is a picture of the experiment done in the lab where we switched from NOR to NAND. Both are fundamental gates by just switching a small threshold, and so this was giving NOR response for a bit. Then we switched it, and really quickly, with almost no latency, it started behaving as a NAND. You can actually also get different logic operations by just varying the number of iterates. So say this one was the first iterate giving this. Here I can say second iterate, and you try to do the same thing and see what logic it gives. So here are the iterates of the map. The first one gave you these two gates. The second one gave you all these. And the higher the iterates, you can get more gates. This part is not very useful for applications because, it's going to be more sensitive and you don't want this. But however, up to 4 or 5, it's very nicely implementable in the lab. Okay, so now not only can you get the first chaotic iterate, you can use a few subsequent iterates to get an even richer variety of reconfigurable logic gates. And this is a company which is developing this particular idea based on some of our patents. And the first generation was out quite some time ago. It's now got sold to ARM based in the UK, in Cambridge. But essentially, it works from this idea and has made a chip which would be more reconfigurable and would allow more flexible architectures. Okay. Now, in the last 15, I suppose I have 15 minutes or so, right? Or maybe 15, 20 minutes. Let me just switch gears and try to indicate to you another idea. And this is, again, nonlinearity, because I do nonlinear dynamics, is central. No running away from that. But in the first bit, noise was not a player. Okay, we didn't deal with it. It was perfectly deterministic, no stochasticity. But now we address noise. And that was because a lot of people kept asking us, an issue which, of course, people have to confront, that as things are shrinking, as devices are getting, more complicated, people are encountering fundamental noise characteristics. They can't wish it away, they can't suppress it, they can't eliminate it. So what do? Is there something which we can do which tricks noise to work for us? So the cooperative behavior between noise and dynamics is what my next 15 minutes will be about. And then I will, wrap up. So the thing is that there is a history to it. Noise and nonlinearity have often got together and produced counterintuitive physical phenomena. One of them is stochastic resonance. So by this, there are many, many ways of addressing it, but let me put one concrete thing out there. In stochastic resonance, you can add an appropriate amount of noise to boost the signal. So if you take signal to noise ratio, so which you can say is some measure of information transfer, this is maximized in the presence of a non-zero noise. So you might think that noise is getting in the way of signal and reducing it and making it worse. However, it was found that a little bit of noise actually facilitated either the detection or the transmission of signals. So this was demonstrated in many, many physical systems. And some of it was even used by people outside physics, like geologists. And of course, engineers apparently knew this. They called it dither noise, and they were using it without doing the analysis. And even biologists have been interested in it because subthreshold information can be transferred in the presence of noise. So what we tried to do was to search for reliable logic circuits which exploit now the nonlinearity in the presence of the noise floor. So if we can understand this cooperative behavior between the device noise floor and the nonlinearity, then we could try to use that to design and develop some computational concepts which could help, to actually do better in whatever noise is ambient. Okay? So we investigated this, and here is an executive summary. We took a nonlinear system which had stable states. We hit it with a stream of input signals. So this could be anything. There's I1, I2, two input signal, whatever the world gives you. And we found that in an optimal band of noise, the output was the most consistent as a logical combination of the input signal. So basically, if I wanted to make a logic gate of the nonlinear system, it would work most reliably when there was a bit of noise. And so we call this logical stochastic resonance. And now this word is everywhere. And though we had borrowed from stochastic resonance in like inspiration, and of course we are doing logic, so logical. I'll give one simple example just to, if everything else, at least one example I should give, which is simple. So consider a nonlinear dynamic system, which is some f of x, which say has two wells. To make, we have done it for many, many things, but I'll give the most simple one. I feed it with a low amplitude, subthreshold, low amplitude signal, because you want low amplitude to give you large effect. That's the whole idea of getting a good engineering return. And there is some noise as well. So let me specifically take I1 and I2, two inputs, and they add up to a pulse. So this system can see, since there are two independent signals, it's a three-level aperiodic, because they can add in any way waveform. And so, for instance, I could take a simple nonlinear system like so, with two wells, bistable, with say one at near -1, one at +1. So this is a schematic. These are the input bits feeding into the nonlinear system. There is some noise. And what is coming out of it is the system is jumping from what was one well to the other well. So 0 output to 1 output, etc. in response to this input bits in accordance with the truth tables of logic. Okay. So the noisy system is forced by this and is giving a logic output consistently. And here is a picture. And, even if you forget everything, maybe you could keep this one thing to carry back. This is that nonlinear system for 3 different noise levels. Okay. When it's very noisy, it is all a mess. This is no good. No engineer will touch a system which is hopping back and forth so randomly. Okay. It can't give any consistent output, and it will not serve in any fashion. So this is out. Let me jump to the low noise. You may have thought low noise is good, but low noise is still not good, because you see the system is getting stuck at the wrong output because it doesn't have enough kick to switch wells when it has to switch wells. So sometimes the same input level, say this one is the same input level. This little pulse here is the aperiodic 3-level input pulse. So this input is the same as this input, but this output is stuck here and this output is stuck up there. So one is giving 0, one is giving 1, not at all good again, not reliable. However, if in the presence of moderate noise, it is perfect. So it actually jumps exactly when you want it to jump and no other time. So the crucial observation is that the logic output is obtained consistently and robustly only in this optimal window of noise. So for very small, very large noise, it does not give consistent logic output, but in this reasonably wide band of moderate noise, it produces the desired logical outputs absolutely consistently. And this has been verified in many experiments, including some from our group as well. Okay. You can also add a little bias to the same equation, the old one, but now I've put a plus C. That's just some bias which changes the symmetry. It's a DC asymmetrizing bias, you can think of it. Very easy to do in experiments. You just add some, something. And but why did we do this? We found that when we added this, we could go back to our old idea of morphing or reconfigurable logic. And this one, by just tweaking it or changing it, we could not only get consistent logic, we could also change the logic function. So here is a summarizing picture, which took a lot of time to produce though, which is the probability of obtaining these logic operations. This was done over 1 million runs just to see that, we were actually getting consistency. And we have on this y-axis, the asymmetrizing DC input, just a constant bias. And on the y-axis, on the x-axis, we have the noise. Okay. On one side, we give NAND, other side, we give NOR. So we find that for some C, it gives a perfect NOR. For some other C, it gives a perfect NAND. But all of it is in this window of noise, which is moderate. Okay. So we can also morph between the logic responses by just adjusting the bias in this window. Now, a couple of just pictures to say that this was done in various experiments. I'll just indicate one or maybe 2 of them. One is a nanomechanical oscillator, which operates in the nonlinear regime with 2 different vibrational states coexisting. And what we made out of it was a noise-assisted, reprogrammable, again, between, say, NOR and NAND, or OR and AND, nanomechanical logic gate, essentially based on the same principle of logical stochastic resonance. So this was fabricated in the lab of Mohanty in Boston University. And so he had this actually ready, and we said, just do the experiment. And he did it again very quickly. And this is the experimental trace. Many others are there in this nanoletters paper. But this is AND, and this is OR or NOR. And again, you see the lower panels is large noise, bad. Higher panel is low noise and sometimes gets stuck in wrong areas and doesn't respond properly. And the middle panel was really good. So the same thing which we expected, we actually found. And as I said, just a couple of things I'll leaf through. Another example was using synthetic genetic networks as parallel logic gates. And here again, we used now a noisy biological system. Okay. And this was work done with Ando and Kazuo Aihara. Ando was then a PhD student, and he was, essentially sort of working with me at that point. And this is our cover page, which I like because it is such a pretty color scheme, which was the artists of EPL had done a very good job. So here we had done something where we had done two complementary gate operations in parallel. So now we have gone one step further. Not only are we switching, because we had two of these systems, we tried to see if we could get parallel computation out of it. So maybe say one is doing OR, maybe one is doing AND, maybe one is doing XOR, one is doing AND, in which we can get maybe bit by bit addition. So basically we then showed that we could do parallel operations by using two of these systems. And this was the electronic analog of that system. Actually, a slightly hard experiment to do, but they managed to do it. This was low noise, as you can see in the traces. It's stuck up here or stuck down here. That is no good, right? I mean, the input is going up and down. Output is just 0 always or 1 always. Bad. But then he put some noise, and then it started switching exactly according to the truth tables. Okay, so very good agreement between the circuit measurements and the prediction. And there are a couple of popular articles on this. One was written in Physical Review Focus on our work, which is very readable. The one in Science News actually is probably even nicer because I think this was, both of them are very readable, and there are more popular versions of what I put more technically here. Okay, there is illustrative work from other groups as well. Some people use colored noise, some people put time delay, some people have used other information-based measures, tried to decrease bit error rates, etc., etc. There are experiments too using different kinds of diodes, using VCSELs, laser systems, other kinds of mechanical oscillators, NEMS, MEMS, other resonators, and even some thin film systems. Okay, so there's a lot of groups around the world who have done this. So I just want to ask, I will actually maybe perhaps somebody could tell me if I have 5 minutes, or should I wrap up now? Should I take 5 more minutes, or is it okay? Maybe Professor Dhiman could tell me. Okay, I don't hear anything. So okay, so let me in 5 minutes wrap this up. Okay, so what I just wanted to tell you in 2 minutes now, very quickly, is that you can now also put together the ideas of which we had of chaos and logical stochastic resonance together. How? There are systems where the chaotic attractors are multi-stable. So you hop not between two steady states like in the well, which I showed you, well here and well here, and but there are chaotic attractors, and you can hop between those. So now you are getting logic operations from chaos, but you're also hopping. So it's put everything together. And we sort of put those two concepts together, chaos computing and logical stochastic resonance, and got this trajectory to switch between chaotic attractors, again, appropriately, in the presence of inputs and moderate noise to get perfect logic output. Okay. And the interesting thing here was that the input signal could be exceedingly small, like 10 to the power minus 3, okay, compared to the size of the attractor, which would be of order 1. So which implies that such a small change in the system yielded a significantly different dynamical outcome. So some people call these things tipping points. So you essentially push your attractor to a point where it's going to jump with the smallest shove, okay? And so in engineering terms, what it does is, use of this complex attractors is it gives you, so here is a picture of it, hopping between chaotic attractors now. And what does it do? What it does is, it manages to give you, for an extremely small input, a significantly amplified output, okay? So the executive summary of this is, the noise flow can aid reliability of logic operations even when it is based on switching of more complex attractors, like a chaotic attractor. Can't get more complex than that. So we call this generalized logical stochastic resonance. And also the amplitude of input signals could be very low, and I don't know how, even smaller than noise strength. We found this even in experiments. So like in this experiment, for instance, we found that we could use an input signal which is 100 times smaller than the typical experimental noise. So it was quite amazing to us. We couldn't quite account for it, but it was there. We didn't expect such a big effect. And so basically small changes could give significantly different outcomes, and that is what we want to use. Okay, so this is my last slide, and I hope I managed to convey to you that nonlinear systems, which actually are widespread in nature, not just in natural systems, but also in the laboratory and in engineered systems. So what we tried to do was to use these systems, exploit the nonlinearity, the richness of the dynamics, to design a slightly different computing device. And this device would be more flexible, would be reconfigurable, and would allow a kind of pattern generator for the logic. So rather than suppress the chaos, we have turned the question and attempted to use the opportunities given by chaos, okay, to design the responses we wish. Okay, and the last point was, I also indicated directions, trying to use the interplay of noise and nonlinearity to obtain reliable logic operations, which we call logical stochastic resonance. Okay, so that's it. Yeah, thank you.
So thank you. Hello, so I'm audible.
Hello. Yes, I can hear you. Yes.
So thank you, Dr. Sinha, for nice and knowledgeable talk. I think audience might have enjoyed it. This is altogether different. You see the area
From
physics for all of us, but you
right.
every nitty gritty, very right from the beginning, not from the scratch. So you taught us very nice things of chaos and how to utilize chaos for the benefit rather. Instead of ignoring.
Yeah.
So now I invite all the audience to please do ask any query, because it's a very interesting talk, and we are going to host it on the web page. So
Right.
it is available to all of the physics community
Right.
across India and so. So any questions, Pankaj? Now you please do manage the rest part of it. Conduct question session as well.
Yeah.
Okay. Thank you very much, ma'am, for this wonderful talk. So this talk is open for all. So if someone have any query, can unmute.
Right.
And ask.
I did see a question in the chat box.
Yes, sir, I have it. Yes, ma'am.
Yeah, that you can take.
So it says how threshold factors, right? I can read it actually. How threshold factors are, I suppose, linked with physical system in experimental situation is in the chaotic chip or chaotic processor. Did I read the question right?
Yeah.
I think so, right?
Yes.
Yeah, right. Yeah. So as I was probably, there were many ideas, so I probably didn't give enough time for that. So what happens is that this threshold is what is determining the nature of the logic functionality. So if I change the threshold, so the threshold, once I put it, it's fixed. Okay. So suppose I say I want my system to be a NOR gate. Then I will put a certain threshold. Then suppose because I want a flexible hardware, suppose I want it actually to behave as an AND gate, all I need to do is fix another threshold and I will get it. So basically, if I may just go back for 1 minute to my old slide. So I would actually, so this is the one. So here the threshold comes in, X star, so that is my threshold. Okay, so and f of x is my chaotic processor, because that is the chaotic function. And as I can change this X star, I should be able to get different things, and or X or NAND or not, whatever. Okay, so that is my knob. That is my logic knob in some sense, which I can tweak. So if I look at it this way, so I will think of it as a morph. Well, they used to call it in chaologics a morph control. So basically that is your tweak, which will make your chip behave in some logic function or the other logic function. And you can keep changing it at will. So that is the idea. That is where the threshold comes in. And of course, in most cases, like in say Murali's experiments or Raja's experiments, they were actually just a voltage. I mean, they were using some standard precision clipping little module there, and it was very simple to change. And apparently in Morai's chip in Japan, he too tweaks the voltages in some fashion. I don't know what's in that because it's classified for them there. Yeah. Yeah, so I see another question here. Should I take it? I see another. Yeah. So I see another question here, which is okay. It says, can we apply this chaotic system, I suppose, to quantum systems to deal with noise? Okay. So this is a very hard question. And if I were honest, I would say, I don't know. And I honestly don't know. However, I'm thinking about it. It is true, because of course we would all like to deal with quantum systems in some ways. When I was, in the earlier part of my career, I was very much into quantum chaos, or the quantum implications of classical mechanics or classical chaos was very important. However, our understanding there does not still allow us to do this. So I am, it is an open question. It is a good question. The only part which seems to work is that there are some systems which are definitely, the phenomena is completely quantum mechanical in origin, but have effective classical formalisms, which one can use to some extent, okay? But I still don't know the noise question. I have some friends also who are trying hard, but we have not cracked it, yeah.
Okay, so we have a question from YouTube stream that Tamanna is asking, is there quantum chaos also?
Yeah, yes. So right. So I'll let me take a minute to answer that. So though it is not related to the talk, but it's definitely a good question. So I should answer it. So the point is that as you know, the way I defined it, the way it is rigorously defined, we need trajectories. Okay, so your momentum and your position is exactly defined in a trajectory. And of course, you know that you can't do that. So you can't take the definition of chaos in classical system and just without thinking transport it to quantum system. Will not work. However, what a lot of people have been trying is to find a way to characterize quantum systems whose classical analog is chaotic. So what do I mean by that? You take say atomic and molecular system, or some or nuclear system, something which has classically you think its analog, if you manage to write a Hamiltonian, could solve it, would be chaotic. You stare at the quantum mechanical system and see if you spot any differences. And two things were very important. One was level statistics. So it was found that systems with classical analogs that were chaotic had statistics which were matched with random matrix theory like GOE and GUE, and otherwise they gave Poissonian style. So people looked at level statistics as a sort of signature of quantum chaos. Okay, by level statistics I mean you make a ladder of quantum states and look at the how they are distributed, and what their spacings are, and what the probability distribution of those spacings are. There are more important things like delta 3 and other random matrix theory, which are more accurate, of course, which you can do. But the idea is the same. You look at the quantum mechanics still, okay? And the second thing which Gutzwiller had done, which we can push to some extent, but is hard, is something called a trace formula, which relates density of states to a classical object on one hand side, and people try to make connections and see what the quantum analog of a classical system, which would have chaos, what would it look like? Okay, so quantum chaos is a study in things like this. People have looked at wave functions also and found things called scarred wave functions to understand it. A lot of this also is done by atomic and molecular physics, because they have a lot of data which is spectra, and they would like to see that. And they also have classical analogs and semi-classical mechanics. Okay, so it has nothing to do with the talk, but I hope I gave some indication. Yeah. Right. Yes.
Good afternoon, ma'am.
Hi. Good afternoon.
Is Moore's law a challenge in dealing with the chaotic theory? Moore's law.
Moore's law, yes. Yes, of course. I mean, everybody is trying to beat Moore's law, of course, in some way or the other. Yes, it is, of course, a challenge, because for two reasons. One, of course, is the fundamental noise floor, which is a thing. The second thing is power. So even if you make it very small, you don't, it also should, it shouldn't take too much power. So, you want to go to nanowatts or something, because otherwise your system will heat up. So it doesn't make sense to have a really small system which is getting so hot that you need a big fan. You see, it's like saying, I'll have maybe a quantum computer, but it takes up a room, though it's a small thing, but so you actually want a system where you are packing in stuff, but it should also not heat up. So it is, of course, a challenge, and it is of course mostly an engineering challenge. So for us to the engineering team, which obviously I'm not a part of, but our idea fed into that. So they have been, of course, trying very hard to make it everyone's challenge is smaller and less power. Yeah, but of course I mean, I'm sure everyone knows that it has to have a hard cutoff at some point. It cannot sustain. Yeah, unless one. And this too, I mean, our method too will have the same issues. I'm not saying that it will bypass them. The only extra thing I'm giving is that with the same space and the same power, you will be able to be more flexible. So maybe you can do something like, an ASIC, like, optimize your hardware for a specific purpose, like, application specific circuit. Or if you want to make something like a FPGA or out of it, except FPGAs might, do it with connections. Here you do it with the logic functionality. So you're not trying to get that much smaller, but you're trying to get more versatile. I don't know if does this answer at least a little bit of what you asked?
Okay, so there is one last question from the group that you have defined chaos as a primal apparatus of the universe before the thing comes into existence, or you have mentioned before ordering. So the question is, everything is created from chaos.
Yeah. No. So I definitely didn't define that. I'm just saying that the word chaos had some commonplace meanings. So we have some meaning for it now in English language, but even before the English language came, even in ancient Greek and ancient Chinese, apparently there was a word which is essentially the same word, chaos. And they had some meaning for it. So it is the old Greek meaning. It is not the technical meaning, of course. And somehow they had this meaning, like, like a primeval, some, soup of, pre-order was their thing. What I had found interesting was that when people told me that in China also they had this, and it had the same meaning. So, so I thought I'd just put two one East and one West country to show it. But of course, these are colloquial meaning in the language, much before commonplace English language meaning. And of course, much before the technical meaning. Yeah. The interesting thing is that you take some word which has some meaning to us, like in the dictionary, and sociology pushes it into a terminology which is like a technical term. How it happens, because this has happened in living memory for us. It is interesting to see from the science sociology
How
that
can we
it.
calculate the entropy of the chaotic signal?
Okay.
Sorry.
Ma'am, there
So
is a
sorry,
question from
I heard
YouTube.
some. Yes,
Okay,
I
yes.
didn't
There
hear
is a
it.
question from YouTube that Abhinav Chaudhary is asking, how can we calculate the entropy of chaotic signals in the communication systems?
Yeah, right. So there are of course many measures one could use. One of the usual ones is something called KS entropy, the Kolmogorov-Shannon entropy, and people have been doing that, especially engineers who are interested in looking at they were actually, some of them were interested in noisy channels, etc., etc. There are a whole host of measures, but they are all very well defined quantities which you can define from a time series. So given a time series, you can write, I don't have a tablet on the side to write the formula for you, but you can look up Kolmogorov-Shannon entropy. KS entropy is one of the well-used ones. There are very, very many analogous quantities, like of course correlation integrals, which are again related to this as well. And these are all popular, but at the end, or rather in the beginning, all you need is a time series. And what is more interesting is that even if the time series came from a high dimensional system, sometimes you can work with just the scalar. So for instance, people will say the weather is high dimensional and chaotic, but I have just say a temperature time series. Every day I take the temperature, or every hour, every minute, and I have a time series, a series of numbers. And people will use that and time series methods to get correlation integrals and KS entropies out of it. And there are very well defined methods for that. Yeah. In fact, there are black boxes now. I think I'm sure you'll get some, some module, it's like a packaged algorithm almost at this point. Yeah. You just need a time series. Yeah. Okay.
So is there any
If
question?
anyone want to ask from the participant, please.
Okay.
Or Pankaj, you can conclude now, I think.
Okay, sir. So thank you very much, ma'am. So now I would like to invite my PhD colleague, Virender Thakur. So please deliver the vote of thanks. So Virender, please.
Sorry, you had asked me to unshare the screen. Have I managed to unshare?
Yeah,
you can unshare.
Yes.
A very good noon to one and all present here. This is Virender Thakur, and it gives me a great pleasure to deliver the vote of thanks. I would like to thank Professor Sudeshna Sinha for giving this scintillating talk, and I'm sure that it will help many students to do better in this field. Secondly, I would like to pay my gratitude to IPA for giving us the opportunity to host this event, and also Department of Physics for making this event happen. Last but not the least, I would like to thank all the participants from various institutes and universities for their participation. I would like to thank Ravinder Shinde for his constant technical support. Once again, thank you all. And for the concluding remark, I would like to invite Professor Shashi K. Diwan again.
Okay. No, I don't have to say anything, but I thank Professor Sudeshna Sinha again. And I would like to acknowledge, you see, the initiative started by Professor Bandana from TIFR. She basically initiated, and she set a proposal. And it's a wonderful having ma'am, you, and your talk is a wonderful. People enjoyed as it appears from the question. There might be so many questions because many people are joined this talk through YouTube channel. So
They are
anyway,
welcome to write email to me. They are welcome to write email to me. Yeah.
of course. So anybody has any question, you can directly address to ma'am. Her email ID is available on the website of Aisar Mohali. So you can visit there and write. So thank you very much, ma'am. And I thank other my colleague from Jalandhar, Dr. Mittal, H.M. Mittal, and Dr. Harleen Dhaya, Professor Manoj Sharma from Thapar, and many other people might have joined us from the other places. So I thank all of you for joining, and thank you very much, ma'am, once again. Thank you. So, okay.
Thank you. Okay, so I'll leave the thing now.